Greetings from Cal Poly State University in San Luis Obispo, California. My name is Hunter Francis, Director of the Center for Sustainability in the College of Agriculture. This video is a continuation of a 6-part series on soil health, whose original funding was provided by the USDA's Western SARE program. Today we're going to be looking at the plant essential nutrients in soil, how they flow and cycle, and some factors that are related to their availability. Nutrition is the science that studies the interaction of essential substances constituting food sources in relationship to the reproduction, growth, maintenance, health, and disease of an organism. It includes how food is taken in, absorbed, assimilated, and excreted. This chart shows the 17 elements that are normally considered essential to plants. As we pointed out in Chapter 3, carbon is sometimes the forgotten nutrient and is a big driver in the soil system, providing an essential food source, one that determines a lot of what happens in the microbiome. The first 3 elements listed, carbon, hydrogen, and oxygen, however, are plentiful in the environment and easily brought into the plant through air and water. The 3 macronutrients, nitrogen, phosphorus, and potassium, have traditionally been the focus of fertility programs and, when limited, can severely limit plant growth. What are sometimes called the secondary macronutrients, calcium, magnesium, and sulfur, are likewise essential, but usually needed in smaller quantities. The micronutrients depicted at the bottom of the chart normally serve as cofactors or catalysts that help to facilitate important reactions within plants and are therefore also necessary, but are needed in much smaller quantities. This list contains all of the macronutrients plus a few others, showing what proportion of plant material they normally constitute, and also how they are brought into the plants in terms of their ionic form. Nitrogen is brought in as nitrate, phosphorus and sulfur as phosphates and sulfate, and calcium, magnesium, and potassium as positively charged cations. Over 80% of plant tissue is comprised of carbon and oxygen, with the macronutrients all being under 5% each, and micronutrients well under 1%. The science of plant nutrition got a big boost in the 1800s. At that time in Europe, Central Europe in particular, a revolution in organic chemistry was underway, and many organic compounds now commonplace, such as aspirin, were discovered at the time. One of the most brilliant chemists of his day, Justus von Liebig of Germany, did pioneering work to illuminate the nature of how plants receive their nutrition, and made his ideas public in his 1840 book, Organic Chemistry and Its Applications to Agriculture and Physiology. Von Liebig was one of the first to understand that plants bring most of their nutrition into the roots in a soluble form, and made the observation that we could furnish the soil with such soluble nutrients to help boost the nutrition available to plants. He disproved what was then called the humus theory, the idea that plants somehow eat organic material to help provide their nutrition. He came up with the theory of the law of the minimum, which is still used today and states that the growth of a plant will be limited by the most limited nutrient in the soil, which is essential to plant growth. He also made the observation that 3 of the most necessary plant nutrients from the soil were nitrogen, phosphorus, and potassium, NPK. The importance of the legacy of his work is unquestionable, and it spawned the agricultural research stations that have now become common in countries around the world. He also trained some of the first agricultural scientists of the USDA, which was founded in 1860 by Abraham Lincoln. One thing that is less known about von Liebig is that later in his life, by the 1870s, he ironically became a big champion of organic matter, noting that while it is true that plants do not eat organic matter, and while it is also true that we can support their growth by providing valuable soluble nutrients, He recognized that organic matter had several other important roles in creating a healthy environment for plants, and was a big proponent of what Albert Howard later called the law of return. In other words, the idea of replenishing residues back into the system to help make the best use of them and to keep soils fertile over the long term. The image of a barrel, with its staves representing plant essential nutrients, is a common way of illustrating the law of the minimum. The stave, or the slat, that is short or lacking, will be where the vulnerability lies in terms of providing a sufficient level of nutrients for plant growth, here represented by the level of water in the barrel. Where the staves or the slats are short, there's a deficiency. Another historic discovery of profound consequence was the synthesis of ammonia through the Haber-Bosch process, discovered in the first decade of the 20th century, also in Germany. Ammonia thus produced could then be turned into ammonium fertilizer. This enabled industry to take very plentiful nitrogen in the atmosphere and turn it into a plant-available form that could be used in agriculture. The ammonium produced was also important in the munitions industry, and that was the first significant application of the invention. As the demand for chemical fertilizer increased with expanding populations, however, the nitrogen-producing factories were increasingly dedicated to the production of fertilizers, making once what was a scarce nutrient relatively abundant and inexpensive, that is, at least while oil was cheap. The Haber-Bosch process is actually highly energy intensive, and this is why nitrogen fertilizer prices are so closely tied to energy prices, and also why the process therefore raises some sustainability questions in terms of resource use for the future. The other important thing to realize is that through this invention, carbon was effectively severed from nitrogen, in the sense that it was now possible to provide and meet a plant's nitrogen needs without having to add organic residues, in which carbon and nitrogen are tied together. While this was a welcome advance because it meant that nitrogen could be supplied much more easily without having to deal with bulky and cumbersome organic materials, it also made it easier to deplete the carbon in soils because it no longer had to be added along with the nitrogen that was bound up in organic inputs. As far as how nitrogen actually makes its way into the plant, it and several other soluble nutrients like calcium, magnesium, and sulfur will freely move with water in their dissolved form to the plant root. As water flows to roots, nutrients carried by mass flow are simply carried along with it. Less soluble nutrients, such as phosphorus and potassium, tend to migrate across gradients of concentration, as depicted here, where you have a high concentration of an element on the left that impels movement towards an area of lower concentration, somewhat similar to mass flow, but aided by the tendency for the ions to seek an equilibrium in terms of concentration within the system. More recent studies, and this is very new, have shown that in certain cases plants are able to take in larger compounds than was once thought possible, building on the idea that plants can only take in nutrients as soluble ions. This chart depicts the entry of ammonium and nitrate into the plant in ionic form on the right, but indicates, if one looks towards the center of the chart, that monomers, or simple compounds, can in some cases circumvent the breakdown process, here in the middle of the chart, that converts such compounds into ionic forms that can then be consumed directly by plants. In the case of nitrogen, this could mean the direct entry of an amino acid into the plant, an amino acid being a monomer or building block of a protein. While this type of absorption may have implications for nutrition in the future, it is still understood to be the exception rather than the rule of how nutrients enter plants. Regardless of how they are brought in, When nutrients are deficient, signs of their deficiency often manifest and are observable in the plant. There's an art and science to being able to identify nutrient imbalances through plant coloration, growth patterns, and other observable indicators. We will not be focusing on that here, but this chart highlights some of the main things that one might look for in trying to decipher visually what nutrient could be the cause of a growth problem harming plants. Yellowing of leaves and sometimes redness could be caused by deficiency of several nutrients. Necrosis refers to plant tissue that has died and is usually brown. One of the reasons that we've included this chart was to make the point that nutrients have different degrees of mobility within the plant as well as within the soil. Yellowing of leaves is common for both nitrogen and sulfur, seen here if one looks within the first 3 rows of the chart. This is one of the most common deficiencies that one might look for, since both nitrogen and sulfur are macronutrients. However, nitrogen deficiency will first show signs in older leaves because nitrogen moves much more freely within a plant. Thus, new growth will rob nitrogen from older tissues, making them turn yellow in color. Sulfur, on the other hand, is not mobile within a plant and will remain stuck in the old leaves, and thus yellowing will occur at the tips of the plant in the case of a sulfur deficiency. When we talk about the availability of nutrients, and in this case talking about those nutrients that are bound up in organic tissues, whether they are of plant, animal, or microbial origin, we need to think about where such nutrients are positioned in an ongoing oscillation between an immobilized or mineralized form. When plants are bound in tissue, they are immobilized. As they are broken down after death and digested by the microbiome, those nutrients are then released in a mineral or mineralized form. Here we are looking at some organisms, bacteria, a fungal root, an amoeba, that contain nutrients within them, such as proteins that contain nitrogen. When that nitrogen is released, it might be found in the form of ammonium or nitrate, as shown here, which then means it is available for plant uptake. Carbon in the immobilized form might be in the form of a carbohydrate or perhaps a protein or a fat. However, when carbon is mineralized, it is respired out and given off as carbon dioxide. Plants can then take in that mineralized form and re-immobilize it back into tissue, in the case of carbon by fixing it into tissues via photosynthesis. Fixation in this case would be tantamount to immobilization. Understanding this cycle is becoming increasingly important as more attention is given to the fact that the microbiome and soil organic matter are a storehouse not only for carbon, but for other nutrients such as nitrogen and sulfur. Predicting the contribution that may come when those immobilized nutrients are released into their mineral form is important in estimating the soil's potential contribution to nutrition and should be a part of a fertility assessment, particularly when working with a more biological or organic approach. This schematic is an artist's representation of the nitrogen cycle, with nitrogen entering the system at several places in organic form through plant residues, animal manure, and so on, and thus being added to the organic matter pool. As that organic matter is digested, the nutrients are mineralized, and in the case of nitrogen, first made into ammonium and then further nitrified into nitrate. Both of those are then available for plant uptake and are immobilized once again into plant tissue. There are 3 main ways that nitrogen can be lost from the system, as shown by this picture. One is simply by leaching, which nitrate is particularly prone to given its negative charge and high solubility in water. But nitrogen could also be denitrified, as shown on the right, particularly in anaerobic situations, because the bacteria responsible for denitrification are anaerobic. In situations where high pH exists, such as in basic soils, compost piles, or manure, nitrogen is also easily lost through volatilization. This is when ammonium reacts with hydroxide or OH molecules to form water and ammonia gas that can then easily escape the system. Sulfur, with its negative charge and relative solubility, follows a cycle that's very similar to nitrogen's. Here you can see plant and animal residues coming in on the left and made part of the organic matter pool, which can then be mineralized by microbes into sulfate that is available for plant uptake, but which could also be lost through leaching or volatilization, like nitrogen. The phosphorus cycle is somewhat different because phosphorus is much less soluble than nitrogen and sulfur. On the contrary, phosphate ions are quick to react to form insoluble inorganic forms of phosphate that are less prone to leaching. However, like any nutrient, it is vulnerable to runoff through erosion, and like nitrogen, can be a significant contributor to pollution of waterways and thus contribute to a potential eutrophication hazard. As we learn in Chapter 2, the prefix eu refers to good in Greek, and troph means food. Nitrogen and phosphorus provide good food for algae and water that can grow out of control. When they die and are decomposed by microbes in the water, the microbes have a tendency to utilize all of the oxygen, thus creating what's called an anoxic zone, and resulting in fish kills and the notorious dead zones that are common in polluted water. As we also learned in Chapter 2, the bacteria and fungi within the microbiome in the soil can play a very important role in helping to mineralize phosphorus by excreting compounds that help to solubilize the inorganic forms, thus producing a mineralized form that is available for plant uptake. In thinking about how quickly immobilized nutrients might be made available for plant nutrition after having been mineralized by microbes in the soil, the ratio of carbon to nitrogen serves as an important predictor. Microbes need both carbon and nitrogen as food and energy sources in order to undergo their metabolic activities. Microbes have a carbon to nitrogen ratio of about 8 to 1. That is about 8 parts carbon to 1 part nitrogen in their tissues in terms of mass. They have a tendency to want to pull materials out of the soil system down to that ratio, but in order to do that, they need enough nitrogen. Therefore, when a material of much higher carbon to nitrogen ratio is added, the microbes grab nitrogen from elsewhere in the soil system to be able to digest the carbon. Thus, residues with the higher carbon to nitrogen ratio, in this case, things like various types of straw, will be harder to digest and will need more supplementary nitrogen. The fresher residues, like cover crops and manure, usually have a much higher level of nitrogen within them, and thus have a lower carbon to nitrogen ratio. Through the digestive activities of the microbiome, these materials eventually are brought down to create a soil CN ratio, usually in the neighborhood of about 12 to 13. This chart depicts what might happen to available nitrogen, such as nitrate within the system, here in the center of the chart in green, when a residue of high CN ratio is added into the system. The microbes will happily eat up all of that carbon, but in order to process it, they will have to pull from the nitrogen pool within the soil, thus immobilizing it. They are assimilating that nitrogen into their organic tissues. This creates, in this case, a dip and nearly a total consumption of all of the nitrogen within the soil system. However, once microbes have burned through the carbon available in the residues, they eventually will die, their populations will decrease, and the nitrogen tied up in their bodily tissues will be re-released into the soil in a mineral form, therefore adding nitrogen back into the available nitrogen pool. The resultant amount of nitrogen within that pool will presumably be higher than the nitrogen that we started with on the left, because nitrogen has in fact been added into the system through the residues. It just had to be digested first, and this created a temporary immobilization of nitrogen. This is another set of charts which are illustrating the same dynamic, but with two different types of residues. The one at the top shows the addition of a residue with a relatively high carbon to nitrogen ratio, in this case about 60, shown by the green line starting point at the left. And as we saw in the last picture, there is a dip in the soluble nitrogen level in the soil as microbes start to digest the carbon in the material that's been added with the help of soil nitrogen. This results in the depression of nitrogen. As the mineral is digested, more and more of the carbon is burned off, thus resulting in a lowering of the C to N ratio of the residues. Eventually, that CN ratio is pulled down beneath 20. In the lower picture, a residue of much lower carbon to nitrogen is added, in this case under 20. And while there's still a slight dip or depression in the the nitrate available in the soil, it's much smaller and lasts for a much shorter time because the residue has had enough nitrogen contained within it for the microbes to be able to digest it. Very little nitrogen is needed from the soil system. In this case, again, the CN ratio of the residues in the soil is brought down beneath 20. In the lower picture, there is perhaps a higher contribution of nitrogen at the end because the residues that were added originally had a higher percentage of nitrogen within them and thus contributed more. As a general rule of thumb, one can expect significant immobilization of nitrogen when adding a residue with a CN ratio higher than 20. This is much less of a danger when the residue that is added has a CN below 20. In this case, there may be a temporary and minor immobilization of nitrogen, but it will have a much smaller effect on the nitrate pool within the soil system. This chart does not depict the carbon to nitrogen ratios of the organic inputs listed, but it does indicate the percentage of nitrogen contained within each. As might be expected, flesh materials and blood, such as fish meal or bat guano and blood meal, have a relatively high percentage of nitrogen. Somewhat surprisingly, the pelleted chicken manure has one of the lowest percentages of nitrogen in the items listed. I'm including this here because it lists materials that were used in a research experiment we'll look at next. In looking at how the nitrogen from the various materials was released in this study, you can see that over an 8-week period in both cooler and warmer temperatures, the materials that we mentioned with the higher percentages of nitrogen, such as the guano, fish powder, and blood meal, released their nitrogen at a much quicker rate than did the pelleted poultry manure, which had a much smaller percentage of nitrogen in it. This is a reflection of the rate of mineralization based upon the nitrogen content of the starting material. When adding materials of relatively low nitrogen composition, one can expect that nitrogen will be released slower. In this case, the pelleted poultry manure, which had only 2 to 4% nitrogen, only released 20% of the nitrogen after 8 weeks. On the other hand, the guano, fish, and blood meals had released well over half of their containing nitrogen. Another common factor that needs to be taken into consideration when considering the availability of nutrients in the system, in particular the micronutrients, is the pH of the soil. This representation of the solubility of nutrients at different pH levels is a common one. What it shows is that many of the macronutrients are most available in the middle of the chart at a relatively neutral pH. Molybdenum at the bottom would be an example of a mineral that can be problematic when pH is on the low side of the spectrum at the left, but not vulnerable to being tied up by chemical reactions when pH is above neutral or basic on the right. Iron, which is also a plant essential nutrient, is an example of the other extreme, being very available at low pH, but increasingly unavailable in alkaline soils at the right. Aluminum follows the same pattern as iron, and in acidic soils, such as in warm regions that receive a lot of precipitation, and where aluminum can build up and predominate on exchange sites, this can even lead to aluminum toxicity, where abundant aluminum is readily available in acidic soils. Aluminum and iron toxicities do not present problems in higher pHs because they precipitate out at high pH and are not available to plants. The precipitating out of calcium in high pH is of particular concern to growers in arid regions such as the West, where soils are more basic. A few quick notes here about how nutrient balances can also affect the availability of nutrients for plant uptake. In the first case, some related elements undergo a certain competition with each other, such as in the case of elements with similar charge. Both calcium and magnesium, two secondary macronutrients, have a 2+ charge. However, calcium is needed in the higher percentage than magnesium. Likewise, potassium with its +1 charge is needed at a much higher rate than similarly charged sodium. Conditions can vary, and soil reports will normally tell you how well you are doing in the case of such nutrient ratios. But one would normally want calcium and potassium to be available at least at twice the rate of magnesium and sodium respectively. Another thing that you will usually find on soil reports these days is base saturation, which refers to the saturation of basic cations, in other words, ions with a positive charge that are commonly found on cation exchange or CEC sites. The elements calcium, potassium, magnesium, sodium, and hydrogen are all cations that you will find on CEC sites. And it may well be, in terms of overall amounts, that you have plenty of each. If so, the so-called sufficiency level of each nutrient would be considered adequate. They would not be considered a limiting nutrient. It would not present a problem in terms of deficiency. However, there is a theory that is prevalent in some soil circles and which is gaining acceptance that says that the relative proportions of the basic cations, even if sufficient, matters. Exact recommendations can vary, and they're somewhat dependent upon environmental circumstances, but in general, to meet most nutritional requirements, it is recommended that calcium represent about 60 to 70% of the total cations available, magnesium between 15 to 20%, and potassium between 3 to 5%. Sodium, which can be detrimental, and hydrogen, which can lead to acidity, are understood to be in the best place when representing under 3% of those common cations. You will note in this case that the recommended ratio of calcium to magnesium is about 4:1. Again, exact recommendations may slightly vary. In California soils, which can be basic, and where calcium can be tied up because of pH, sometimes the recommended percentage of calcium may be over 70%. We've talked a lot about deficiencies, but some elements will create problems in excess and even become toxic to the system. This is an issue of nutrient balance also, and often the case because they are outcompeting other beneficial nutrients. On the bright side, for many nutrients, the microbiome can provide an ameliorating and decidedly positive role by helping to hang on to plant essential nutrients, in particular metals like calcium and magnesium, by producing organic compounds that are capable of hanging on to them. They do this with a molecular structure that creates claw-like tentacles called ligands, the blue lines here. The ligands can grasp onto those metal ions, here represented by the letter M. The Greek word for claw is chela, C-H-E-L-A, and this phenomenon is called chelation. It is the grasping and holding of ions by molecular compounds, thus preserving them until that time that they are needed for plant nutrition. At that time, the plant will signal its need, and the nutrient will be released in exchange for another ion. Chelates are known for helping to increase the bioavailability of many essential nutrients. This is a more complex diagram depicting the interactions between a fungal hypha and minerals in the soil. At the bottom of the picture on the left are mineral complexes such as chelates that hang on to metals depicted again with an M, and that can be released when a root or hypha secretes an organic acid that releases the metal. This is similar to what can happen to cations hanging on to a clay or organic matter particles, as here on the right, and that can be exchanged for hydrogen, thus making them available to the plant or other organisms, indicated here as biota at the top of the picture. Thus, chelates, mineral complexes, exchange sites on minerals and organic matter can all be reservoirs of plant essential nutrients that are released in exchange for chemicals exuded by plants and microorganisms. Last but not least, and something that could be talked about at length, is the detrimental presence of salts in a soil system. Salt is a common impediment to healthy soils, particularly in the West and dry areas where evaporation is severe. Soils with high salt content hang on to water and make it difficult for plants to access it, and can present toxicity problems in and of themselves. A soil is considered saline when it is having a salt content of over 4 decisiemens per meter, indicated by the red arrow here. As that salt content increases, especially beyond, say, 8 decisiemens per meter, plants will become increasingly sensitive to it, although in varying degrees depending on the type of plant. Salt content and all of the things that we've discussed above need to be considered when we are thinking about the health status of our soils.